整包档案。我说先把它放桌面上。好。
这样你可以跟他继续跟他分享。
应该有，正在录制，有。上面这个啊，不要
按，我这样子不能按。
哦 ，OK， 好。需要用麦克风还是应该没有关系？老师刚刚有用，没有用。好，
可以用你讲比较大声。
好 ，OK。
麦克风就可以讲1小时。
对。
现场就。
Okay, so today I'm going to talk about the second homework 2 and the question 5. Oh, how? So for the question 5, we are going to train a cat dog classifier using ResNet50. And in this question, we'll have 6 parts. Okay, so here I will briefly introduce the question. And so first, the objective, we're going to learn how to train a ResNet50 model to classify images of cats and dogs and learn how to deal with imbalanced data. And the model we're using is ResNet50. So it has 2 characteristics. The first one is residual learning. It avoids degradation problems. Okay. And so the second characteristic is bottleneck. It allows us to build a deeper network without additional parameters. Okay. So we can take a look at the figure here. This is a residual block. And in this residual blocks, it has 3 convolutional layers and 1 shortcut. So this shortcut, it can pass the input feature maps from here to here, and combines with the feature maps from the convolutional layers. So this shortcut, this technique is called residual learning. And then next we can take a look at here. The input feature maps is 256 channel. But here we use a 1x1 convolutional layer with 64 filters to decrease the number of channel from 256 to 64. And then we use these 64 channel feature maps, use a 3x3 convolutional layer to extract features. And after that, we use another 1x1 convolutional layer with 256 filters to enlarge the channel number back to 256. So this type of structure is called a bottleneck. And so here, this is the basic characteristics of ResNet50. And after knowing this, we can take a look at the figure on the right. And this is the structure of ResNet50 model, and it is adapted for this case to we want to classify cats and dogs. So first, we can see the input is an RGB image of 224 by 224 by 3 channel. And this image will be input to the 7 by 7 convolutional layer with 64 filters and strike 2, and getting 112 by 112 by 64 channel feature maps. And next, we'll use 3 by 3 max pooling layer to downsample the feature maps. And then we're going to 4 sections of residual blocks here. We can each sections have different colors. So this blue one is for the first section. And in this section, we have 3 residual blocks here and getting 56 by 56 by 256 channel feature maps. So in these 3 residual blocks, it all has a 1 by 1 convolutional layer with 64 filters, 3 by 3 convolutional layer with 64 filters, and a 1 by 1 convolutional layer with 256 filters, and a shortcut. This is a residual block, and we'll have 3 of them in this section. And after using these 3 residual blocks to extract features, we'll go into the next section, the yellow one. And here in this section, we have 4 residual blocks here, getting 28 by 28 by 512 feature maps, which contains the higher level features. And so the structure is quite similar to the first section. So in the first residual block here, it has a 1 by 1 convolution layer with 120 filters and strike 2, and 3 by 3 convolutional layer with 128 filters, a 1 by 1 convolutional layer with 512 filters, and a shortcut. So this residual blocks, we have a strike 2 convolutional layer here. So it will downsample the feature maps. So we can see here, we have 56 by 56 in width and height. And after we use the strike 2 convolutional here, we will get 28 by 28 in width and height. Okay, so this is the first residual block. And next we'll have 3 identical residual blocks. And all of these 3 residual blocks have 1 by 1 convolutional layer with 128 filters, 3 by 3 convolutional layer with 120 filters, a 1 by 1 convolutional layer with 512 filters, and a shortcut. So this is section 2. And for section 3 and section 4, we have a very similar structure, but with different number of filters and different number of residual blocks. So you can take a look at the difference in these sections. So here, after these 4 sections of residual blocks, we'll get 7 by 7 by 2048 feature maps, 2048 channel feature maps here. And we'll go through a global average pooling here to calculate the average values of these 2048 feature maps. So we'll get 2048 values, and it will be input to a FC layer, fully connected layer with 1 node to classify the image. And the output, finally the output is a confidence value ranges from 0 to 1. So what does this mean? Like, for example, here we have an image of cat, and its class label, for example, is 1. And the output, the confidence value should be close to 1. And that will be correct. So this confidence values means how confident the model thinks the input is a cat image. And for example, if we have another image of dog and the class label is 0, so the confidence value should be close to 0. So that's what what this confidence value means. Okay, so this is the structure of ResNet 50 model, and next we'll go to the data set we're using. So we're using cats and dogs data set, and it is modified from Kaggle cats and dogs data set. The data type is JPG images, and we have two classes here, cat and dog. And you can download the data set from the FTP, and it is right here. The path is download homework HW2, and the data set is a zip file. And in the zip file, it has 3 folders. The first one is training data set. It has 16,200 JPG images in total. However, the data set is imbalanced. So this means, for example, you will get fewer images for cats and more images for dog. That's called imbalanced data set. And you will have to train your ResNet 50 model using this data set. But later I will tell you how to deal with the imbalanced data set, so you don't need to be too worried about it. Okay, so next you will get a validation data set, which contains 1,800 JPG images, and you will need use this data set to validate your model. And the last one is inference data set. It has 10 JPG images in total. It is for testing the inference function in your GUI program. Okay, so next we'll proceed to the requirements here. And so for this question, you will need to make a GUI program like this. You'll have buttons on the left and image on the right, and you can run inference and show the predicted class label here. Okay, so and the other requirements are you need to train ResNet 50 models with TensorFlow or PyTorch. And every chart should have a chart title. For example, like you draw a bar chart, you need to give us the chart title and axis titles telling what does the chart means. And the last one is you have to organize the files in this structure. So the first one, this is a project folder, and then file name is HW205, and your student ID, your name, and the version. And in this folder, you will have first the folder called model to put your trained models here, and another folder called inference data set. And it's you just copy the inference data set, download from FTP to here. Okay, and then you will need to put a main.py file, and this is the code for your GUI program. And train.py file, this is the code for model training. And you can put some other files or folders you may need in this homework. But you need to follow this structure here, model inference dataset, main.py and train.py. Okay, so next we're going to talk about 6 questions here. The first question is load the dataset and resize images. So at home, you will need to load the training dataset and validation dataset. And here are some functions you may need. Like for TensorFlow, you can use this image dataset from directory function to do that. And for PyTorch, maybe you need to use this dataset, this function or this class to implement to load the training dataset and validation dataset. And after loading the dataset, you will resize images to 224 by 224 by 3 channel. It is an RGB image. So here are also the functions you may need for TensorFlow or for PyTorch. Okay, so when the demo, you will click on the button Show Images in your GUI program to load the inference dataset, resize images to 224 by 224 by 3 channel, and get 1 image from each class in the inference dataset, just like this one image for cat and one image for dog. And after getting these images, you will show them in a new window. And you can use matplotlib pyplot functions to show these images. And here are some functions you may need. So the output will be look like this. We have a new window and showing two images, one for cat and one for dog. Okay, so this is the first question. And the second question is plot class distribution of training data set. So at home, you will load the training data set and iterate through the data set to count the number of images for each class. So you will count, and in this case, we have cat images and dog images. So you will count how many images are there for the cat, for the class cat, and how many images for the class dog. And after counting the numbers, you will plot the class distribution, just like the example here. We have x-axis is cat and dog, and the y-axis is number of images. So we can see cat have 7,200 images here, and dog have 10,800 images here. You have to plot this kind of class distribution figure and save the figure. So when the demo, you just click the show distribution button and show the saved figure in a new window. So this is question 2. And for question 3, we're going to show the structure of ResNet 50 model. So at home, you will need to build a ResNet 50 model, and you can use for TensorFlow, you can use this function to build a model. It will define the convolutional layer, max pooling layer, or some that kind of layers for you. And for PyTorch, you can use this function. And after building the model, we'll replace the output layer to a FC fully connected layer of one node with sigmoid activation function. And for TensorFlow, you can use this tf.keras.layers.dense, this function to do that. In PyTorch, you can use torch.nn.linear function and torch.nn.sigmoid function to do that. And the first step is to run the function to show the structure in the terminal. And for TensorFlow, you can use this summary function. And for PyTorch, you can use torch summary to do this. So this will be the output for the output you will see. And this is the structure of ResNet 50 model. And so when the demo, you will click on show model structure, click this button to show to run a function and show the structure in the terminal. So the output will be look like this. And next we'll I'll introduce how can you read the structure. So it will list in this this output, it lists the each layer of the ResNet 50 model. And so this this column is for the layer name, and this column is the feature map shape. So it is BHWC, and it means batch size, height, width, and channel. So in here, batch size, we don't need to define it in while coding this function. So we will see none here, but we can see the height and width and channel for the feature map. And this column is the number of parameters here. And this column is the layer that connecting to. So so this means like for this, the second row, this layer is connecting to input 1, 0, 0. So it connects to here. This is what it means. And so you can look at, read this output, this structure, and you can see this input layer, it is actually the input here in this diagram. And this, the convolutional layer is actually the 7x7 convolutional here. So you can read it carefully, but I think this process is quite tedious, so you need to pay attention to read the structure. Okay, but this is how you read the structure from the function. Okay, so next is for question 4. We have to set up 2 kinds of loss functions to train 2 ResNet 50 models. And so at home, you will set up focal loss and binary cross entropy, these 2 loss functions in the code for model training. So the train.py file. And in TensorFlow, you can use tfa.losses.sigmoid focal cross entropy, this function to define focal loss, and tf.curious.losses.binary cross entropy to define binary cross entropy. In PyTorch, you can use torchvision.ops.sigmoid focal loss to define focal loss, and torch.n.function.binary cross entropy to define binary cross entropy loss function. So, and this is because we're using focal loss here, so focal loss accepts 1 confidence value to calculate the loss. So that's why we need to replace the output layer of ResNet 50 model to a FC layer of 1 node and with a sigmoid activation function. Okay, so please, maybe you need to follow this hint here, so or to get a correct result. And then after setting 2 loss functions, you will train 2 ResNet 50 models with these 2 loss functions. And in TensorFlow, you can use this model fit function. And in PyTorch, you will need to write a for loop to train the model. And you can refer to the tutorial here. So this is so when the demo, you will show your codes about loss functions in train.py. And like this is the example here. So you will have the first loss function and the second loss function here. So at home, you just define these 2 loss functions. And when you want to train the first model, you just comment out another loss function to run it, to train the model. And for us, like for here, for the example, you want to train the first model with focal loss. So you comment out the second loss function and train it. And after you want to train another model, you just comment out the first loss function and use the second loss function to do that. And also you can follow the hyperparameter settings here shown in this example. Okay. So next I'm going to talk a little bit about what is focal loss. And this is the definition of focal loss. It is FL means focal loss. FL of PT equals minus alpha t multiplies 1 minus PT to the gamma, how to say that? To the power of gamma. Oh, I will say that again. Minus alpha t multiplies 1 minus PT to the power of gamma multiplies log PT. And so first we'll take a look what PT is. So PT equals P if the class label is Y. So for example, the class label for cat is Y is 1. So it means if the input image is a cat image, we'll use P to for P the PT equals P, and otherwise the PT equals 1 minus P. So like if our input is a dog image, the PT equals 1 minus P. Okay, so here the Y is the ground truth class label. It should be 0 or 1, and P is the model's output confidence value for the input with class label Y equals 1. So in this case, it is the confidence value for the image as the input. So this means if our input is a cat image, we'll use P to calculate the loss. And otherwise, we'll use 1 minus P to calculate the loss. And then we'll see here is the alpha t, and alpha t equals alpha if y equals 1. For example, the input image is a cat image, and alpha t equals 1 minus alpha if the input image is a dog image. Okay, so this alpha is a class imbalance weighting factor, and it is usually set to 1 minus the frequency of y equals 1 examples. So in this case, it could be the 1 minus the frequency of cat images. And here we have a small example to show how to calculate it. And for example, we have 30 examples here with y equals 0. So 30 examples for dog images and 70 examples with y equals 1. It means 70 examples for cat images. So the frequency of cat images is 0.7. So the alpha value will be set to 1 minus 0.7 equal. It is actually 0.3 here. So you can follow this this step to set up alpha value. So that's why we need to calculate how many images are for cats, how many images are for dogs. It is for setting the alpha value here. And finally, we have another last notation is gamma, and it's the focusing parameter. It is used to help the model focus on hard examples. Okay, so the focal loss, it mitigates class imbalance problem by assigning more weights to hard examples and less weights to easy examples. And also, I want to mention that focal loss is for binary classification. For example, foreground and background, face or non-face, or for this case, cat and dog. Okay, this is the focal loss. Okay, and the fifth question, we're going to compare the accuracies of two less than 50 models using the validation data set. So at home, you will need to validate two less than 50 models with the validation data set, and then plot the accuracy values with a bar chart, just like this chart. And so the figure will look like this. In the x-axis, you will this is for binary cross entropy. This is focal loss, and the y-axis is accuracy. So you will evaluate it and plot the accuracy values with a bar chart. So you can see here, the focal loss, it has the accuracy of 86.4, and binary cross entropy has accuracy of 84.7. So you may see this kind of difference, but actually it will based on the hyperparameters or some other settings you use. So you may not see this kind of the difference here, but just don't need to be too worried about it. Just give it give these two loss functions a try and show us the difference. Okay, so after plotting the accuracy values, you will save the figure. So when the demo, you just new window, just like this. Okay, so let's go to the final question. And you will need to use a better trained model to inference and show the predicted class label. So you will have 6 steps here you may need to follow. And the first one is load the trained model. You can use these functions. And the second one, you just click on the button, load image, like here, load image, to select one image arbitrarily. So you will click this button, it will show a dialog, and you can choose, you can choose the image you want to run inference. And after clicking this button, you select the image and show the loaded image in the GUI program, like this one, and resize the image to 224 by 224 by 3 channel. And then after this, you click on button inference to run inference on the resized images. So you can, for TensorFlow PyTorch, you can use these two functions to do that. For TensorFlow, you just run predict step, and for PyTorch, you just pass the image when calling the model object to run inference. For example, your model is called train model here, and you just call this train model in this way to run inference. And after finish the inference process, you need to show the predicted class label. So how do you decide which label you want to show? You can use a threshold for the output value, because the value we get from the model is actually 0 to 1. So you'll define a threshold to decide the class label. For example, if the output value is smaller than the threshold, you define it to cat. And if the output value is bigger or equal to or bigger than the threshold, then you will define it for dog. And the threshold you can, for example, use 0.5. Okay. So when the demo, you just need to repeat the process, repeat all the process here. And yes, that's for the last question. So this is question 5. And so anyone have questions here?
Output is only one class or two classes?
One.
So it's switch.
Yeah, so you need to use a threshold. Yes. Does anyone have questions? Okay. Guys, yeah. Oh.
Because we don't have too much time. Time is up. So today our class will be here, up to here. Okay, so that's it for today's class. Thank you, and take time for your